Hi everyone. This talk is about our recent progress on simulation-based hardware Trojan threat assessment. We call it Silicon Critique. Nowadays, IC design flows are mostly fabless. The mask production and chip fabrication are largely outsourced. Fully in-house supply chains can hardly be found. Here you can see a typical IC production process. The chip designers finish logic design and physical design in-house and then send the GDS2 layout to the external foundries, which is called tape-out. However, this creates opportunities for untrustworthy foundries to make malicious hardware modifications, which is known as fabrication time attacks. Previous works demonstrate various ways that fabrication time attackers can insert a hardware Trojan into a finalized IC layout. Hardware Trojan has become a major hardware security concern. They can serve various purposes, such as functional change, denial of service, or information leak. A hardware Trojan consists of a trigger and a payload. The trigger activates the payload when some attack condition is satisfied, and the payload serves to execute the actual attack. The figure is an example of a simple Trojan, whose effect is to leak the keys that are not encrypted. Though we have witnessed diverse fabrication time attack measures, they tend to share one similarity. The attackers require free spaces and routing tracks on the finalized physical layout to place and route the appended Trojan. Today, researchers have developed two main classes of defenses against fabrication time Trojan: prevention and detection. Unfortunately, the stealthiest Trojans are proved to be able to bypass all these defenses. But prevention techniques are preferable in recent studies, and design time layout adjustment has shown its potential to frustrate foundry-level Trojan insertion. It is natural to ask how we can evaluate the effectiveness of the design time protection like layout adjustment without trying to attack the strengthened layout in a real foundry. Well, several security metrics have been proposed to measure the susceptibility of IC layouts to fabrication time Trojans and quantify the coverage of design time defenses. While defined and computed individually, these metrics estimate the amount of replacement sites or routing channels in specific regions of an IC layout, regardless of the properties of specific Trojans to be injected. The quantization results are deterministic, calculated by the geometric information of the physical layout. Accordingly, we conceive such metrics as geometric only. So, what are the problems of these geometric-only metrics? We demonstrate the limitations of previous metrics with the toy case study. Suppose the attacker would like to insert an XOR gate into a 4-bit adder to flip one output bit, and we have two versions of adder layout with different core utilizations. Unrelated wires are hidden for better visualization. Previous metrics would indicate that version 2 is more secure than version 1, since version 1 has more white space around security critical cells. However, in reality, the insertion of Trojan gate in version 1 results in longer Trojan wire length than version 2, and version 1 shows better Trojan detectability for delay analysis than version 2. Now we can summarize the limitations of previous geometric-only metrics. First, they provide insufficient prediction fidelity because they are essentially first-order estimations of available placement and routing resources. Second, they are Trojan oblivious, regardless of the specific type of Trojan to be inserted. For example, In the case study, if the Trojan cell was slightly larger and could not fit in layout version 2, the version 2 would be more secure instead. And last, they consider no analysis of the Trojan insertion due to their first-order nature. Therefore, in this work, we propose Silicon Critique, a simulation-based, Trojan-aware framework for layout vulnerability evaluation. The basic idea of Silicon Critique is to simulate the black box fabrication time Trojan attacks with white box design time techniques. The Silicon Critique evaluation flow can be divided into three phases. The first is netlist preparation. It extracts the netlist from the tape-out ready layout, retrieves security critical signals in the design, and appends synthesized Trojan to the extracted netlist to produce a collection of attack schemes corresponding to different Trojan inserted netlists. The second phase is Trojan insertion. We implement the attack schemes generated in the last phase at layout level in batch. Thanks to the engineering change order or ECO operators in commercial CAD tools, we are able to mimic the stealthiest foundry-level Trojan attacks by optimally place and route Trojan cells and nets while maintaining the existing layout. The last phase is side channel analysis. We determine the layout vulnerability based on Trojan detectability, which can be quantified as the variations of some timing or power-related metrics after Trojan insertion. Specifically, for timing, besides total negative slacks or TNS that indicates overall timing condition, we define maximum path delay rise, or MPDR, of a given layout as the maximum critical path delay increase after Trojan insertion, which magnifies Trojan impact and improves detection sensitivity. Similarly, we use total power and the maximum regional power rise to indicate power variation. We evaluate the effectiveness of representative design time defenses on 4 real-world designs against 4 reported hardware Trojan respectively. We diversify the attacks by varying Trojan complexity, properties, and footprints. For the assessed defenses, we use Silicon Critique to evaluate the original design and the designs enhanced by 3 major defenses. Layout compression blindly increases core utilization to compress free place and route resources. Built-in self-authentication occupies empty layout spaces with tamper-evident logic. Our previous work, GDS2Guard, rearranges the layout to eliminate spatially continuous empty regions without increasing placement density. The last 2 defenses are target security critical cells. For timing analysis, we show the change of the 2 timing metrics, TNS and MPDR after Trojan insertion. The distribution of the metric values is derived given the various attack schemes. We can draw the following conclusions from the results. Layout compression provides insufficient protection with poor design performance, and defenses targeting security critical cells show better detectability efficiency. Moreover, tailoring defenses to specific types of Trojans is more effective. For example, GDS2Guard leaves no space for the placement of sequential Trojans with large flip-flop cells. As for power analysis, The results show similar variation relationships with time. More difficult the Trojan is to place and route, more power will be consumed, given longer routing distances and added buffers for time enclosure. We also evaluate A2, still is the known hardware Trojan, with the standalone case study. Since the digital part of A2 consists of simply two combinational gates, geometric-only metrics make no sense because 100% layout occupation is impossible. The results show that all the defenses fail to isolate the Trojan because the timing and power variations are too small to be differentiated from the noise. In conclusion, Silicon Critic can inspire future design time defenses to focus more on Trojan-aware and routing-centric enhancements. We also realize that design time defense is unlikely to completely block Trojan insertion. Instead, increasing attacking difficulty is more meaningful considering the tight turnaround time for the foundry. Silicon Critic can be extended to customize side channel metrics, other processes, CAD tools, and even the attacker's perspective. Our future work is to resolve the impact of process variation on simulation accuracy compared with the actual fabrication. And that's all for my presentation. Thank you for listening. We have open sourced the implementation of Silicon Critic. Thank you.